Today's lesson is on channel routing. Chapter 10 of the McEwen Hydrologic Design text explains how to perform channel routing. There are two overall learning objectives for this module. The first is evaluating the theory behind channel routing, which will be performed by looking at a stream section. And second, evaluating procedures for calculating the output hydrograph based on both the convex and Muskingum methods for channel routing. Prior to developing methods for channel routing, it is essential to evaluate the channel itself. A plan view of the channel is provided, and a control volume established for this analysis is shown. The upstream and downstream flow rates are depicted entering and exiting the control volume respectively. The control volume itself represents the storage of the channel. This storage will allow for the output flows within the channel to be both attenuated and translated, as explained in the prior video. The flow rate within the channel can be determined based on continuity, where flow rate Q is equal to velocity V times the cross-sectional area A. A rating equation is determined by using a velocity meter and surveying techniques to measure the various depths in the channel flow. Cross-sectional surveys are conducted at the upstream location noted by AA. You can see that the channel geometry and depths can be determined. Then, a power relationship is developed that evaluates discharge as a function of stage or depth. The input flow rate, Q in, and H represents the inputting discharge and the respective flow depth or stage. A and D are constants developed from the power relationship. An additional cross-sectional survey is taken at section BB, the downstream location. For practical reasons, the overall geometry does not change much. If the geometry did have a significant change, it would be necessary to break up the channel reach into more sections. Thus, the schematic shows section BB looks similar to section AA. Since it's important for evaluation of channel routing, it should be noted that the upstream and downstream cross-sections do not vary much, and the constants A and D are the same. Similarly, evaluation needs to be performed on the overall storage. Storage is a function of depth as well. However, the constants for the power relationship are B and M. Since it's a function of depth similar to discharge, it is important to note that storage, since it is a function of depth similar to discharge, storage is also a function of your input and outputting flow rates. The overall storage thus is determined as S equals X times S input plus 1 minus X times S output, where S input represents the storage associated with the inputting flow rate and S output represents the storage associated with the outputting flow rate. X is a weighting factor that will allow us to put certain weights on the inputting versus the outputting flows. Recall from the previous slide that the input storage is equal to B times the depth raised to the M power, and remember that both B and M are constants. In addition, the inputting flow rate is equal to the depth, or is equal to A times the depth raised to the D power. By rearranging this equation, depth is equal to the inputting discharge divided by A, all raised to the power of 1 divided by D. Next, by plugging in the depth into the storage equation, we can rearrange the equation such that the storage input is associated with B times the quantity of Q input over A raised to the MD power. We can further simplify this equation by pulling out all the constants and setting them aside and keeping the Q input raised to the MD power by itself. By putting all the constants together, we can further simplify the equation by saying that this inputting storage is associated with the constant K times the flow rate raised to the MD power. A similar procedure is done for the output. The only difference is that the storage is a function of the output flow rate. The following equation can be used to evaluate storage. Storage is equal to X times K times the inputting discharge raised to the MD power plus 1 minus K times 1 minus X times K times the outputting discharge raised to the MD power. The first method to discuss is the convex method. The convex method uses the overall storage equation developed in the previous slide. We can evaluate the convex method by making some assumption. The first assumption is X is equal to 0, which indicates the storage is only a function of the output flow rate, not the input flow rate. Next, M divided by D is equal to 1. Therefore, the storage in our system is equal to the constant K times the outputting flow rate. The convex method further simplifies the hydrologic budget as described in the previous video. I1 minus O1 is equal to S2 minus S1 divided by delta T. It should be noted that I1 represents the Q input at position 1, and O1 represents the Q output at position 1, and so on. During lecture, we will actually do an example where you will understand what position 1 and 2 represent. Therefore, by plugging in the equation for storage into the hydrologic budget, we can represent the inputting flow rate at position 1 minus the outputting flow rate at position 1 is equal to K times the quantity of the outputting flow rate at position 2 minus the outputting flow rate at position 1, all divided by delta T. Since delta T and K are constants, and we can rearrange the equation such that O2, which is what we're trying to find, is equal to I1 times delta T over K plus O1 times 1 minus delta T over K. O2 is equal to I1 times C plus O1 times 1 minus C. Since delta T over K is a constant, we are replacing it with C. So how do we evaluate C? First is the SCS method, where C is equal to the velocity divided by 1.7 plus V. You must know the velocity in the channel. This can be done by taking an average velocity for the various depths and flow rates. Next, we can use the time interval method, which states that the C value is equal to delta T over K. Since we know that K is B over A, we can find it if we have the geometry of both the flow section, or the rating equation associated with the flow rate, and the rating equation associated with the storage, or delta T divided by the travel time based on the velocity method. So what are the steps of solving the convex method? In order to solve the convex method, you must know what the inputting flow hydrograph looks like. Next, you must have an initial output flow rate. And finally, you must have information about velocity and or channel properties. The next method we're going to talk about is the Muskingum method. The Muskingum method uses the same beginning storage equation as developed in our theory. In this method, K is still equal to B over A. M over D is equal to 1. The value of X can vary anywhere from 0 to 0.5. It's no longer 0. Therefore, both the inputting flow and outputting flow are important characteristics. When gauge data is available, the value of x can be determined by performing a regression analysis. But when gauge data is not available, let's assume x is equal to 0.2. And for all examples in class, we will assume x is equal to 0.2. The hydrologic budget states that 1/2 the input flow rate at position 1 plus the input flow rate at position 2 minus 1/2 the output flow rate at position 1 plus the output flow rate at position 2 is equal to the change in storage with respect to time. By plugging in the storages from the above equation, we can rearrange the equation as follows. Next, we can further simplify the equation by putting constants together and putting the outputting flow rate on the left-hand side of the equal sign. This will allow us to solve for O2. The constants C0, C1, and C2 are as follows. They are functions of both K, X, and delta T. It should be noted that it is essential that delta T is provided to you in seconds to solving these equations. If you take C0, C1, and C2 and add them together, it will equal 1. Next, the steps in solving the Muskingum method. You must have an inputting hydrograph. You must have an initial outputting flow rate. You must know the delta T of the hydrograph, and you must solve for K, either by saying K is equal to B over A, or by assuming that K is equal to 60% of the travel time, which in theory is referred to as the lag time, which we'll further discuss in class. During class, we will have examples of both the convex and Muskingum method. It is essential that you bring your equations with you in class so that we can work on examples that will further help your understanding of how to utilize both the convex and Muskingum method for channel routing.